Everybody, welcome back, and we're taking a look at AP Chemistry Unit 1, Section 1, taking a look at atomic structure and periodicity. So we're used to some basic things in chemistry, looking at a periodic table, looking at particles that we find within. There are some other things that we've not covered before in Gen Chem, which is the amount of energy that we find available within the electrons. So this is a new topic for people. It's not too bad because we're taking a look at some basic math, and I'm going to walk you through some examples within this. Okay, Max Planck was the one that was doing most of the work with electromagnetic spectrum, looking at the radiation, and he was working with Einstein's equation of E equals mc squared, and he found that there's actually a wave-particle duality of the electrons themselves. They have energy, they follow the same mechanics as light, and so they also have a mass. And so because they have a mass, they're going to travel at different wavelengths and different frequencies along the way, and we can actually identify different elements based off of that. So it's kind of a cool concept if you think about fireworks, and we take a look at the different colors given off because of the different metals that are found within. Same thing with astronomy. We take a look at different stars. We can tell what the gases are in those stars based on the colors that are given off. So that's the type of thing. It kind of gives us a fingerprint, if you will, of the different elements because of the electrons. And so Max Planck's basically his way to go from his bridge between Einstein's E equals mc squared was through his constant that he discovered of the 6.63 times 10 to the negative 34th. So that is how we get our basically our conversion between energy and the wavelength that's going to be communicated there. Now, when we talk about wavelengths or frequencies, either one, we actually have a chart of this. And you've heard of these things before, like X-rays and UV light and infrared, microwaves, and we have AM and FM radio waves and so on. Those are according to different wavelengths as well as frequencies. Within visible light, you can see, we bring that down a little bit more into the Roy G. Biv, if you've never heard that before. Red, orange, yellow, green, blue, indigo, and violet. And so we see different wavelengths in there, red being a longer wavelength, and then we have the violet going to be a shorter wavelength. Or you can look at it in terms of frequency. Higher frequency is going to be the violet, and a lower frequency is going to be the red. So it depends on what we're looking at. And notice that this particular graphic has our wavelengths in meters. Okay, that's important when we take a look at our equations and the math we're going to do, that our frequency is going to be in hertz and that our wavelengths are going to be in meters. Now, why that's important is because we're generally never given those in terms of meters. We're going to have to convert from nanometers. Okay, so 6.63 is when we're in those units. Now, these elements or these electrons are going to be moving at the speed of light, the radiation is, and so the speed of light is 3 times 10 to the 8th meters per second, and then we can derive that equation accordingly. Okay, we can take that E equals HV also equals E times your constant times the speed of light divided by your wavelength. Okay, so that it's just deriving the equation along the way for those of you who get into that sort of thing. Okay, now from those things, we could take a look at what's being emitted off of there, and we'll do this in lab. This will be like this day 2 when we're taking a look at these things. This is what you do when you look at stars at nighttime and you look through a spectrometer. You can actually see the different wavelengths being emitted, and notice that that's going to be the 700, close to the 700 range, going to be in terms of infrared or close to the infrared. Now, notice that this is photons emitted per nanometer, and our equation needs to be in meters. Okay, so it's just some of the background behind all of those things along the way. The emission spectrum lab is the one that we're going to be doing, and from that we can see different wavelengths. So let's take a look at this first example and how to process the questions. I know this one's already written out for you, but let's take a look at the prompt. We see that we have a blue color in there, so that tells us we're in the visible spectrum heating a particular compound to a certain temperature. When it emits the blue light, we see a wavelength of 450 nanometers. Now, there's one of our key pieces there. Now, this is asking what increment of energy is going to be found from this if we see that we have 450 nanometers. Okay, so those two numbers are saying the same thing. And so the question is, what do I do with this set of information? Well, remember, E equals H times V, and also E equals H times the speed of light divided by our wavelength. Okay, so which one do you think we're going to be using here? We're going to use the one that requires the wavelength rather than frequency. Okay, so we plug in our values. We see that E equals Planck's constant, 6.63, times 10 to the negative 34th. And I'm going to include the units here just so you see how things will cancel out. Joules times seconds. And we're going to multiply that times the speed of light. And so that's 3.0 times 10 to the 8th meters per second. Now, per second means I'm going to divide by second, and we see that notation a lot of times. So that means it's meters divided by seconds. And so there's the top half of the equation, and now we plug in our wavelength. That wavelength is 4.5 times 10 to the second, but be careful, we need to make sure that that's in meters, okay, because we have meters here. So notice that the seconds are going to be canceling out, and we need to divide by the meters. Well, this is in nanometers, and so remember, and this is just a basic metric conversion. Here's the meters, here's decimeters, centimeters, millimeters. There's a couple spaces. Then we have micrometers. Then we have the micro, then the nano right here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different levels that we need to divide by. And so that's where my 4.50 times 10 to the negative 7th meters comes from. I had to divide by 9. Okay, move that decimal to the right by 9, or sorry, we're going to the left to get it up to meters. So we're going to divide by 9. And so that's where my 4.50 times 10 to the negative 7th comes from. And so I plug this into my calculator. I should be getting an answer of 4.41 times 10 to the negative 19th joules. Okay. Now, if I needed this into kilojoules, it doesn't really say either way. Kilo is 1,000th to go from joules to kilojoules is 1,000th. And so that's where I divide 3 more times. So I get 4.41 times 10 to the negative 21 kilojoules. Okay, so it doesn't say which one we need here. I do want to pause for one quick second. You'll see I'll have that number is the one reported. The difference between the two values, this is going to be only 2 significant figures. This one is the one we use that has 3 significant figures. So that's why we're going with 3 significant figures for our answer. Okay, now next question is taking a look at, we have energy given off in kilojoules. Okay, and we're removing 1 mole of electrons from an atom from the surface of a metal. Okay, how much energy does it take? There's our question. How much energy does it take? And let me switch over to my writing tool. How much energy does it take to remove a single electron from the surface? And what wavelength of light would be required from this? And what color range would that be? So we're removing an electron there, and we know how much it takes to remove 1 electron. So if you go back to your conversions of the mole, we remember that 1 mole is 6.02 times 10 to the 23rd particles. So let's take this information. I have 208.4 kilojoules, and I know that that's going to how much it takes to remove 1 mole of electrons from there. How much is a mole? 1 mole is 6.02 times 10 to the 23rd particles. That's Avogadro's number, and that is a review concept. So if that's new to you, we got to get used to the mole conversions with that. We'll do more of that later on, but it is a type of review question. So notice I'm getting rid of that, and I'm saying, okay, how much energy would it take to remove the particles? I have, or the electrons in this case, 3.46 times 10 to the negative 22nd kilojoules per particle. Okay, remember those particles are our electrons. Okay, if I wanted this in joules, then I would just multiply that by 3 then. Okay, so that's where the negative 19 comes from. Now, the reason I want to answer that part about the joules is because 3.46 times 10 to the negative 19th, if you remember, we're using our energy equation of energy equals Planck's constant times the speed of light times our wavelengths. And remember, all of those values are going to be in meters per second and in joules. And so that's why we want to have that first step. And so we have our energy is 3.46 times 10 to the negative 19th joules. Now Planck's constant is going to work, 6.63 times 10 to the negative 34 times the speed of light, 3.0 times 10 to the 8th meters per second. And that will get us our wavelength. Multiply both sides by wavelength, divide by the energy, and we'll find that my wavelength ends up being 5.73 times 10 to the negative 7th. And that's going to be in meters. Okay? If you go back to that chart of the visible light, you'll see that will give us our green light spectrum. Okay, so that's how that works. It's pretty straightforward. Like I said, we're just going through some basic, just plug and chug into the math equations. Now, de Broglie was also the one that was working with the mass. Notice that mass was part of the equation, E equals mc squared. De Broglie was working with the wavelengths in that way and taking a look not at the more of the frequencies and so on that would work with this. Okay, we have a wavelength will equal Planck's constant times mass times the velocity times the speed of light. And so from that, he surmised that our smaller objects have larger wavelengths and the larger objects will have smaller wavelengths. And that makes sense. If you're going to have really tiny objects, okay, they're going to move at a much lot higher peaks and valleys. You know, if you have something really large, it's really hard to move it. If you think about a bowling ball versus a ping pong ball, it's really hard to lift and drop that bowling ball on set wavelengths. You got to move it at smaller wavelengths to make that happen. So let's take a look at this example of comparing two objects, a ball with a mass and an electron. Obviously, the electron has very little mass to it, and so we have two separate problems. Now, this is an AP question, so we want to make sure when they say comparing the wavelengths for things, we want to make sure that we're doing a side-by-side comparison along the way, okay? So make sure we do all the little steps to make sure we get the full points on questions like this. Now, first of all, start with your equation. When in doubt, just write down what we know. Okay, so the constant divided by mass times volume. Okay, now let's take a look at our electron side. Okay, our electron side, we have a mass of 9.11 times 10 to the negative 31 kilograms. Okay, and the speed is going to be going at 1.0 times 10 to the 7th meters per second. That's not quite the speed of light, but it is pretty close to that. So if I'm looking at just the electron side of things and I plug it into my equation, I'm seeing that my electron side of things is 6.63. Okay, here's our constant times 10 to the negative 34. And we have 9.11 times 10 to the negative 31 kilograms. And we have the speed is going to be 1 times 10 to the 7th. Okay, so we see that the electron has a wavelength of 7.28 times 10 to the negative 11th meters. Okay, now I'm not done. Now I take a look at the ball. Okay, the ball wavelength. The information that I have about that one is it has a mass of 0.10 kilograms. So we can compare them side by side. And it's moving at a speed of 35 meters per second. Also, we have two things that are different. It's going a lot slower and it has a lot more mass. So let's take a look and compare those ones. My wavelength is going to be 6.63 times 10 to the negative 34. That's my constant. That's my H value. Its mass is 0.10 kilograms. And it is traveling at 35 meters per second. And so my wavelength ends up being 1.9 times 10 to the negative 34th meters. Okay, now I'm not done. I haven't really answered the question fully because it says compare them. Just showing two values doesn't give me the full points. If this was an FRQ, this would be worth maybe 1 point. But the second point would come with the answering of the question of comparing the wavelengths. And so I would say, based on this information, therefore, the ball has a much smaller wavelength than the electron. Notice it's a direct comparison, and you back it up with the numbers. So this is the second point. When we see questions like that, we have to make sure we're answering the question fully. Be careful that all the math and everything is one point. We want to make sure we're answering the full question. Now, Niels Bohr then did, and this is our bridge when we get to the spectrometry part of it all, Niels Bohr actually contributed to this in a way that helps us to identify the elements, like I said, with the stars or with the different fireworks and so on. We can actually use his concept of the atom. Remember, in the nucleus we have protons and we have neutrons, and on the outside we have electrons. Okay, so that's just kind of the concept of Niels Bohr's model, like this. And when we use his concept, we can actually figure out how much energy these electrons are conserving or using. So say, for example, I added energy to the system. Okay, I heated it up or did something, and there was an electron that was here, but it jumped out. Now, as I take this energy away, that electron will collapse back down and emit that stored energy, if you will emit that as a wavelength of light. So as energy is added, like I said, the electron will jump out and it'll emit the energy when it collapses back down to the ground state. And so there's an equation for actually measuring this, and we use what's called Rydberg's constant. 2.179 times 10 to the negative 18 is that constant in there, but we can use that to figure out how much energy, where those individual electrons actually reside. And then we can figure out, once we know the electrons, where they reside, we can figure out what the element is. Okay, so that basically you just take a look at how many energy levels did it drop. Notice that there is a negative sign right in here because it's giving off that energy as we go. So let's take a look at how this would work with an example and put the equation into play. We're going to calculate the energy as an excited atom has the electron fall from energy level 2 down to energy level 1. Okay, and so we calculate the wavelength of the energy and the type of radiation. So you kind of look at it first, it's like, wait, what numbers do I work with? Well, here's how the equation works. We can calculate the energy of that electron by taking the negative, because it's giving the energy off, of the Rydberg's constant, 2.179 times 10 to the negative 18th joules. And we're going to divide it by the n squared. So what is n squared? Well, n squared is the energy levels. It started at energy level 1, and we're going to take a look at how much it's actually moved. And so minus 1 to the energy level from going from energy level 2 squared. And so we end up with a value at the end. Now remember, there's a negative in here because it's energy given off of 1.63 times 10 to the negative 18th joules. Okay, that's all I need to do with that. Now, if we need to know what type of radiation is needed to do that, well, remember, that's our energy. So then we go back to our energy equation. Energy equals Planck's constant times the speed of light divided by our wavelength. Okay, we know the energy of 1.63 times 10 to the negative 18th. Okay, that's going to be equal to our Planck's constant, 6.63 times 10 to the negative 34, times the speed of light, 3 times 10 to the 8th, and that will give us our wavelength. And so our wavelength ends up being 1.22 times 10 to the negative 7, and that's going to be in meters. Okay? Well, you go back to your electromagnetic spectrum. Oh, that's going to be green light. That's going to be visible light in there. And specifically, we get to green light. So that should give you enough information now to tackle the first section of problems. And there's only 6 problems in there. Pick apart the questions along the way. And then I'll see you for the next video. Good luck.